Welcome back to this advanced manufacturing and process modeling course. So, we were discussing about the transport phenomena in casting. So, process modeling in casting. So, we have discussed about how the discretization schemes are employed to discretize a domain, and thereby we can solve the governing equation to estimate about the temperature and flow parameters in case of coupled heat and mass transfer and fluid flow problems. So, let us start up with the simple algorithm, which is a scheme which is called the semi implicit method for pressure linked equations. So, this algorithm was originally put forward by Patankar and Spalding and is essentially a guess and correct procedure for the calculation of pressure on the staggered grid arrangement. So, that we have discussed earlier, and the method is illustrated by considering the two dimensional laminar steady flow equations in Cartesian coordinates. So, this slide shows you the flow chart of how the equations are solved in case of a simple algorithm. So, we start with the initial guesses of pressure, velocity, u velocity, v velocity, and the field variable for which we are trying to solve, what value we are trying to estimate, and then after the initial guess we solve the discretized momentum equations, which is shown over here. So, you can see, so the guessed value are u asterisk and v asterisk, and then these are a I j and a small I capital J is the coefficient with u asterisk small I capital J, and a capital I small j is the coefficient with v asterisk capital I small j, and then is equal to summation of a n b u n b asterisk plus p asterisk I minus 1 comma capital J minus p asterisk capital I capital J multiplied by capital A I j, which is the coefficient with pressure, and then plus B I j, which is responsible for the source terms. And then so after from solving these equations we get a the value of u asterisk and v asterisk, which is fed to solve the pressure correction equation, which is depicted over here. And after solving this pressure correction equation, we basically get the guessed value of the pressure P prime, and then we basically correct the pressure and velocities using the estimated value of P prime, and then we thereby we can so basically we add P prime with the initial guessed value P asterisk, and then we get the actual pressure that is P I j shown here. Similar technique has been adopted for estimating the actual velocity in the x direction, that is u I j, and also the actual velocity in the y direction, that is v I j. So, we basically so these are the equations that are solved by the solver to estimate the accurate values of pressure and x and y velocity. And then once we get the accurate values of pressure and u v, that means x y velocity, and then our goal is subjected to solve the actual value for the field variable for which we are solving this set of discretized equation, that is phi. So, we start with the guessed value of phi, that is the initial value phi asterisk, and then we solve all other discretized equation as shown over here in this flow chart. So, you can see, and from here we actually get the actual value of the field variable phi, whether it is satisfying the convergence criteria. If it is yes, then we can stop the calculation, we can report the values of the field variable phi and also the velocities and the pressure, and if it does not satisfy the convergence criteria, then the loop goes back. So, if it is no, convergence is no, then again the estimated values of pressure, x velocity, y velocity v, and the estimated value of the field variable phi are set as the initial guessed values like p asterisk, u asterisk, v asterisk and phi asterisk, and then again it is fed to the start state. So, it is fed to solve the discretized momentum equations. So, this is the iterative loop which goes on in case of simple algorithm, and thereby basically we estimate the appropriate values of velocity, pressure as well as the field variable, and that is basically demonstrate the physics of the flow and heat and mass transfer problem which we are trying to solve. Okay. So, So, basically to initiate the simple calculation process, a pressure field P asterisk is guessed. So, discretized momentum equations are solved using the guessed pressure field to yield velocity components U asterisk and V asterisk as follows. So, this is basically the equation you can see. So, A I j A small I capital J and U asterisk small I capital J. The ith and ij locations we have discussed in the previous classes. We have also discussed the grid, so I am not repeating it over here, which is equal to summation of A n b U n b asterisk plus P asterisk capital I minus 1 comma capital J minus P asterisk capital I capital J multiplied by A I j plus B small I capital J. Okay. And similarly for small a capital I small j multiplied by V asterisk capital I small j is equal to summation of A n b V n b prime asterisk plus P asterisk capital I capital J minus 1 minus P asterisk capital I capital J multiplied by A I j plus B I j. So, these are the equations. So, now we define the correction P prime as the difference between the correct pressure field P and the guessed pressure field P asterisk. So, that P is equal to, so the actual pressure should be is equal to P asterisk plus P prime. That means guessed pressure plus the correction pressure P prime. Okay. So, so that after that, so we so similarly we define the velocity corrections, that is U prime and V prime, so that we can arrive at the actual velocity values from the initial guessed velocity values of U prime and V prime. So, we relate the correction terms with the actual velocity values by these equation, that is U is equal to actual velocity in the x direction, U is equal to guessed value of velocity x velocity, that is U asterisk plus correction value of x velocity, that is U prime, and V is equal, that means the correct value of y velocity is equal to the guessed value of y velocity V prime plus the correction term for the y velocity. So, that is V prime. So, this is how they are related, and now basically substitution of the correct pressure field P. So, correct this. So, P into the momentum equations yields the correct velocity field, that is U v. So, please correct this, and the discretized equations above link the correct velocity fields with the correct pressure field. So, how they are linked basically over here. So, that is A I j multiplied by U I j minus U asterisk I j is equal to summation of A n b multiplied by U n b minus U asterisk n b plus P I minus 1 j minus P asterisk, that is the guessed value of pressure I minus 1 j minus P I j minus P I j asterisk into A I j. So, this from here we can simplify it further to the below equation, which states about A I j multiplied by V I j minus V asterisk I j is equal to summation of A n b in the bracket V n b minus V asterisk n b plus. So, this is for the x velocity. So, that is for the x direction, and this is this one the bottom equation for the y velocity. So, y direction. Okay. So, these are the discretized equations that are and then using correction formula we can basically write it as, because we already know that U is equal to U asterisk plus U prime, that the correction suggested. So, here we get U minus U asterisk. So, that means it reduces to U prime. So, that is why from here we can write this as A I j multiplied by U prime I j is equal to, so summation of A n b. So, again the same technique is applicable over here. So, then it can be written as U n prime b plus P, and similarly for pressure correction we know that actual pressure is equal to P asterisk plus P prime. So, then P minus P asterisk is equal to the correction term for pressure, that is P prime. So, then putting that value over here, so then we can write P prime I j I minus 1 j minus P prime I j a I j. So, basically from these two terms, simplifying these two terms, we are arriving at this expression. Okay. And so then similarly for the y component, the similar procedure is followed and this equation is simplified to this equation. Okay. So then at this point an approximation is introduced. So that is summation of a n b u prime n b and summation of a n b v prime n b are dropped to simplify above equations, which are the equations discussed in the earlier slide. So these are the two equations we are talking about over here, and are dropped to simplify above equations for the velocity correction. So, omission of these terms in the main approximation of the simple algorithm. So, we obtain u prime I j. So, because we are dropping these terms, these two terms. So, then if you again look at this, so then this equation, these two equations get simplified further, and it is reduces to u prime I j is equal to d I j multiplied by p prime I minus 1 j minus p prime I j, where because from this equation if you take the value of a I j, because this term is already dropped. So, this got cancelled, this term is cancelled. So, then it is a I j by basically we are getting. So, if we do that, so then a small I capital J divided by small a small I capital J. So, these two terms, so this ratio of these two coefficients is now denoted as a new coefficient, that is d small small I capital J. Okay. So, this is what is shown over here, and this is the same technique applicable for both the x component and as well as the y component, and accordingly from the previous equations we are getting the simplified equations as depicted here. So, u prime small I capital J is equal to d small I capital J multiplied by p prime capital I minus 1 small capital J minus p prime capital I capital J. So, where d small I capital J is expressed as the ratio that I have discussed earlier, and similarly d capital I small j is expressed as this ratio between a capital I small j divided by small a capital I small j. So, ratio of these two coefficients. So, the above equations describe the corrections to be applied to velocities through formulae which gives that. So, basically we have estimated u prime I j and v prime I j. So, now we can guess the actual velocity u I j is equal to u asterisk the guessed value of x velocity I j plus d I j. So, because we know that u I j prime is equal to this one, and we also know that u small I capital J is equal to u asterisk small I capital J plus u prime small I capital J. So, then putting the value of u prime over here, we are basically arriving at this expression. Okay. So, that is why we are writing u I capital J is equal to u prime u asterisk u I capital J plus we are putting the value of u prime I j from here, and then we are writing basically this expression, and similar technique is adopted for the y velocity. So, then v I j is equal to also written as v prime capital I small j plus the new coefficient that is introduced here, that is small d capital I small j multiplied by p prime capital I j minus 1 minus p prime capital I capital J. Okay. So, similar expressions we can also obtain for the velocity at the I plus 1 comma j node, and also for v and the same I j plus 1 node. So, then we can basically write the expression. So, then likewise we can guess the actual velocity values in x and y direction for all the nodes. We can estimate based on this set of discretized equations. So, accordingly the coefficient value, that is small d, also changes, and that also takes the similar form which is shown over here. So, then for x velocity d small d I plus 1 j I plus 1 node capital J is equal to capital A I plus 1 capital J divided by small a I plus 1 small I plus 1 capital J. And similarly for the y velocity we have to estimate the coefficient d capital I j plus 1 is equal to a capital I j plus 1 divided by small a capital I j plus 1. So, this is how we are estimating the coefficients, and then thus we have only considered the momentum equations, but as mentioned earlier the velocity field is also subjected to the constraint that it should satisfy the continuity equation. So, continuity is satisfied in discretized form for the scalar control volume as shown earlier. So, then I mean, so basically the expression looks like this: the rho u a I plus 1 j minus rho u a I j plus rho v a I capital J plus 1 and I mean minus rho v a capital I capital J is equal to 0. So, so substitution of the corrected velocities of equations into discretized continuity equation, because we have already estimated the correct velocity u I j v capital I small j. So, that is what, and also we have also estimated the I mean velocities the velocities at I mean u I plus 1 j and v capital I small j plus 1. So, putting those values of those velocities. So, you please try to have a look at here. So, then I mean what we are trying to do. So, as we know that I mean u is equal to u asterisk plus u prime. So, this is how we are arriving at this expression from this equation. So, then rho I plus 1 capital J multiplied by a small I plus 1 capital J into u asterisk I plus 1 j plus I mean d d I plus 1 I mean into p prime I j minus p prime I plus 1 j minus rho I small I capital J into coefficient capital A small I capital J multiplied by. So, this is the expansion of this term, and this term is the expansion of this term, and subsequently. So, then I mean, so I mean rho I small I capital J multiplied by capital A small I capital J into u asterisk small I capital J plus d I j p prime capital I minus 1 j minus p prime capital I capital J. Okay. And similar technique is followed for these two terms as well. So, you can see the expansion of these two terms over here, and then it is equated to 0. So, basically it is the discretized form of the scalar I mean continuity equation. So, this equation can be further rearranged in the following form. So, you can see from here. So, basically rho the density and the coefficient d, which is the ratio of the I mean capital A divided by small a, as we have discussed over here. Okay. So, I mean so then I mean we can write it as rho d a I plus 1 capital J plus rho d a small I capital J plus rho d a capital I j plus 1 plus rho d a capital I small j multiplied by p prime I j. So, which is can be further simplified as rho d a I plus 1 j and multiplied by p prime I plus 1 small j I mean plus I mean plus rho d a I mean I j p prime I minus 1 j and plus rho d a capital I j plus 1 multiplied by p prime I j plus 1 plus p I mean rho d a I mean multiplied by I mean rho d a at ith and jth location multiplied by p prime I I mean p prime capital I I mean capital I small capital J minus 1 and I mean and then finally I mean we can write plus we can write that plus rho u asterisk capital A I j minus rho u asterisk capital A I plus 1 j plus rho v asterisk capital A for small capital I small j location minus rho v asterisk capital A capital I I mean and plus this should be small j. So, please correct it. So, small j plus 1 and then I mean, so then identifying the coefficients of P prime, that means the pressure correction term, this may be rewritten as small a capital I capital J into multiplied by P prime capital I capital J is equal to small a I plus 1 comma capital J into P prime capital I plus 1 capital J plus a capital I minus 1 capital J and into multiplied by P prime I minus 1 capital J and plus a capital I capital J and then I mean plus I mean P prime capital I capital J. So, I mean so here I mean we have to also add here. So, so here this term I mean P prime I J plus 1, P prime I minus 1 J and yeah. So, this I minus 1 term is there and then I J plus 1 term is also there, I J minus 1 is there and then so here there is one term is appearing to be missing. So, so here there should be a I plus 1 J P prime I plus 1 J plus a I minus 1 J P prime I minus 1 J plus a I J I J J plus 1. So, that term is missing here P prime I J plus 1. No, it is available here. So, it is there and then plus a I J minus 1 multiplied by P prime I J minus 1. Yeah. So, then there should be basically 1, 2, 3, 4 and 5 terms. So, 1, 2, 3, 4 and 5. Okay. So, then it is correct and then where a I J capital I capital J is equal to a I plus 1. So, basically we are clubbing these terms. So, there should be summation of these terms should be equal to the coefficient at the left side, that is a capital I capital J. So, it is equal to small a capital I plus 1 comma capital J plus a I mean a small a capital I minus 1 comma capital J plus I mean small a capital I J plus 1 plus small a capital I J minus 1. So, I mean so and then these are the I mean values of these coefficients that is given over here. Okay. So, this shows that small a capital I plus 1 capital J is equal to rho d a small I plus 1 and then capital J. And similarly, small a I minus 1 capital J is equal to rho d a small I capital J and a small I J plus 1 is equal to rho d a capital I small j plus 1 and a I mean and a I j minus 1. So, here it should be here it should be a small I. No, I mean this is fine because here we have got a I j minus 1. Yeah. So, then it is fine. So, a I j minus 1. So, is equal to rho d a capital I small j. So, and then b prime I j, it is coming from here. So, then b prime I j is equal to rho u asterisk capital A small I capital J minus rho u asterisk capital A I plus 1 capital J and then plus rho v asterisk A capital I small j minus rho v asterisk A capital I j plus 1 small j plus 1. So, this is how the expansion of the coefficients which are simplified in this equation and shown over here. So, then the pressure correction equation is susceptible to divergence unless some under relaxation is used during the iterative process and new improved pressures P nu are obtained with P nu is equal to P asterisk plus alpha P P prime. So the velocities are also under relaxed. So the iteratively improved velocity components, that is u nu and v nu, are obtained from these two expressions, that is u nu is equal to alpha u, that is the under relaxation factor for u, plus 1 minus alpha u multiplied by u n minus 1. Similarly, I mean v nu is equal to alpha u v plus 1 minus alpha v, v to the power n minus 1. Okay. So then where alpha u and alpha v are the u and v velocity under relaxation factors, u and v are the corrected velocity components without relaxation, and u to the power n minus 1 and v to the power n minus 1 represent their values obtained in the previous iteration. Okay. And then after some algebra, it can be shown that with under relaxation, the discretized u momentum equation takes the following form, that is a I j u I j divided by, so this is the under relaxation factor alpha u is equal to summation of a n b u n b plus small p I minus 1 capital J minus small p capital I capital J multiplied by a I a small I capital J plus b small I capital J. So basically we are dealing with the momentum equation plus 1 minus alpha u, again the under relaxation factor a I j divided by alpha u multiplied by u I j to the power n minus 1, and the discretized u v moment, so here it is talking about the u momentum equation at the top in the x direction, and then discretized v momentum equation. Okay. So then it is also similar like this, only we need to replace the u term into v term, and also we also need to change the node location, of course, and then accordingly we have to we can write here that small a capital I small j into v capital I small j divided by alpha v is equal to summation of a n b v n b plus p capital I j minus 1 minus p capital I j into coefficient capital A capital I small j plus b capital I small j. So likewise, so the pressure correction equation is also affected by velocity under relaxation, and it can be shown that d terms of the pressure correction equation becomes d I j is equal to a I j. So earlier, please try to recall that earlier we have estimated the coefficients d I j as only capital A I j divided by small a I j. So now we are multiplying it with the under relaxation factor alpha u. So then similar things are being done for d I plus 1 capital J and d capital I small j d capital I small j plus 1. So then so in this formula small a I small small j and small I a I plus 1 small j small a capital I capital J, and the small a capital I j plus 1, that is are the central coefficients of discretized so are the central coefficients of discretized velocity equations at positions small I capital J I plus 1. So these are basically the nodes I plus 1 j and capital I small j and capital I j plus 1. So this is basically why there is a uppercase and lowercase letter, because of the staggered grid arrangement that we have discussed in detail in the earlier classes. So then basically these coefficients are the central coefficients of discretized velocity equations at these positions, these nodes of a scalar cell centered around P. Okay. So so here there will be a correction. So it is a small a capital I small j plus small j plus 1. It should not be capital J, it should be small j. Okay. Yeah. So so with this we are done with, and this one also need to be corrected. So Yeah, so then we have discussed about the simple algorithm for momentum equation solution. So there are some other algorithms also like simpler. So simpler is just nothing but revised simple. So it is an algorithm again given by Patankar in 1980. So it is an improved version of simple. So in this algorithm the discretized continuity equation is used to derive a discretized equation for pressure instead of a pressure correction equation as in simple. So the intermediate pressure field is obtained directly without the use of a corrective factor. So the velocities are however still obtained through the velocity corrections of simple. So you can understand that it is an improved version of simple algorithm that we have discussed in detail in the earlier slides, and it is a little bit faster process than the simple process, because we are not solving the pressure correction equation. However, for velocities we are still solving the correction equations like we have discussed in case of simple algorithm. And then finally the simplex, that is simple consistent algorithm of Van Durmal and Reitby, which was given in 1984, which follows the same steps as the simple algorithm, with the difference that the momentum equations are manipulated so that the simplex velocity correction equations omit terms that are less significant than those in simple. So, then basically now if we talk about the main features, strength and limitations, we compare these solution algorithms like. So, then simple, that is semi implicit method for pressure linked equations. So, the main feature is relatively straightforward and widely implemented in CFD procedures, and the strengths are effective for correcting velocities, produces savings in computational effort due to improved convergence. And what are the limitations? Limitations are not as effective for correcting pressure fields and also may lead to slower convergence compared to advanced variants like simpler and simplex. And then coming to the simpler, that is simple revised, the main feature is it uses pressure corrections to directly calculate the correct pressure field, instead of relying solely on corrections. So, so basically the simpler algorithm. So here please correct this statement. So it is basically directly calculate the corrected pressure field instead of relying on the corrections, it should be that one. And the strengths are, it provides accurate pressure fields by solving a separate discretized pressure equation, and highly effective in solving momentum equations due to the accurate pressure field, reportedly reduces computational time by 30 to 50%, because we are not solving for the pressure correction. So, however, the limitations are that it requires about 30% more calculations compared to simple. So, then you can see that so although it needs more calculations, however, it reduces the computational time. And then going to the simplex algorithm. So, simplex is a simple consistent. So, the main feature is similar steps like simple algorithm, but manipulates momentum equations to reduce less significant terms in velocity corrections. So, strength, so simplifies the velocity correction equations and focuses on omitting insignificant terms for computational efficiency. Limitation, performance depends on specific flow conditions and degree of coupling between momentum and scalar equations. So, here you can understand that the simplex algorithm basically because it reduces neglects less significant terms. So, that is why it is a faster algorithm and it can take lesser computational time. So, computational efficiency is higher. However, the solution accuracy becomes questionable and it is useful for some specific flow conditions and degree of coupling between momentum and scalar equations. So, so with this we are done with the solution algorithm for the momentum equations, and also similar technique is followed for other conservation equations like conservation of energy, conservation of species, etc. And we have also compared the different solution algorithm, that is simple, simpler and simplex. So, we will stop for this class here, and in the next class we will go into the and take the example of the different modeling approaches for I mean transport phenomena to be solved in case of casting solidification problems. So, thank you till then.